Welcome back. Today we're going to talk about nuclear chemistry. When we talk about nuclear chemistry, we're talking about the stability of isotopes, and this is based on the ratio of neutrons to protons. When the ratio of neutrons to protons is 1 for 1, or 1 to 1, the isotope or atom is very stable. And although most nuclei are stable, some are unstable, and this instability happens when the amount of neutrons aren't equal to the amount of protons. And so when something is unstable, it will spontaneously decay and emit some sort of radiating particle. We use table N in this chapter to explain half-lives, the decay mode, and the nuclide name, and the symbol. It shows the mode and rate of decay, like I said, for select radioisotopes. The half-life explains how long it takes for half of that material of that specific nuclide to decay. Remember, in this unit we set up the table and we had the half-life column, the time column, the mass, and the fraction column. Remember, each table always starts at 0 half-lives, at the original mass, 0 time, and 100%. Transmutation explains or defines the change in the nucleus of an atom, that it converts from one element to another. Transmutation explains when one element changes into a completely different element by a nuclear reaction. This can occur naturally, meaning it doesn't need any outside source or energy, or it can be induced by the bombardment of a nucleus by high energy particles. That's artificial transmutation. The difference between natural and artificial transmutation is in natural transmutation, you only have one reactant, one atom on the left-hand side of the reaction. Artificial, you have at least 2 reactants on the left-hand side of the arrow. Spontaneous decay can involve the release of an alpha, beta, positron, and or gamma particle, or radiation. These particles and their notations and symbols can be found on table O. This unit, we use table N and O most of the time. An important piece to keep in mind is that alpha particles have the greatest mass, and you can see that here under alpha where it has a mass of 4. Gamma rays or X-rays have the highest penetrating power or penetrating ability, conversely, meaning they have a high energy and they can shoot through a pretty thick piece of aluminum foil. Next, in this unit, we fill in nuclear equations. Sometimes they will leave out one product or reactant and you have to fill in the missing piece. Make sure that the sum of the masses, the top numbers, and the sum of the charges on the bottom numbers on both sides of the equation are equal. That's really important. Turn the arrow to an equal sign, add, and fill in the missing value. Additionally, during this unit we talked about radioisotopes that have many beneficial uses. The radioactive isotopes used in medicine need to have short half-lives to be quickly eliminated from the body. I'll say that again. You don't want a radioactive particle hanging around in your bloodstream for too long. That's why they have short half-lives. They get out quickly. Here are 4 that we study. Iodine-131 is used in treating and diagnosing thyroid disorders. Cobalt-60 is used to treat cancer. Uranium-238 is used in geological or rock dating. And carbon-14, one you may be familiar with from earth science, is used in dating the age of living or organic organisms. And finally, the difference between fission and fusion. Fission is the splitting of a large nucleus, like we have here of uranium, into smaller nuclei. Radioactive wastes are produced, which can risk exposure and long-term storage and disposal, and nuclear accidents. Fission is what happens in the atomic bomb, and we all know how that went over at Hiroshima and Nagasaki. It killed a lot of people. In fission, a small amount of mass or matter is converted into a huge amount of energy. Again, think about how devastating the atomic bomb was. And lastly, fusion. Fusion is the opposite of fission. It's when you have 2 smaller hydrogen nuclei coming together to form a helium nucleus. Or in other words, it's 2 smaller nuclei combined to form a larger nucleus. There's no radioactive waste produced during this process, but there is a major problem. You need extremely high temperatures and pressure to perform this, because think about it. You're taking 2 hydrogen atoms that have positively charged nucleuses and trying to ram them together. Well, they're like charges. They're going to repel each other. So you need a really high temperature and pressure to make this happen. Fusion is what happens on the surface of the sun. A small amount of mass or matter is converted into a huge amount of energy. Notice that similarity. Fission and fusion both convert a small amount of mass or matter to a huge amount of energy. That's all nuclear. Until next time.